Hello students, in our previous video we have discussed some of the important problems from the chapter Matrices and Determinants. So today we will discuss some more problems from the same chapter here. Will be if A is a square matrix, A square equal to A, then we have to find the value of I plus A to the power 3 minus 7A. So these are the four options. We have to choose any one of them here by solving the given equation. We use the formula A plus B whole cube because I plus A whole cube is there. So we use this one, A cube plus 3AB into A plus B plus B cube. So using that, I plus A whole cube minus 7A is equal to I cube plus 3IA into I plus A cube minus 7A. Simplify this one, multiplying these two, and A cube can be written as A square into A here. And we know that A square is equal to A. Therefore, finally we got this one, I plus 3A plus 3A square. Multiplication of these two terms, this is these two. Then A square, because A square is again A into A is again A square minus 7A. Or I minus 4A plus A square, 4A square. Again substitute A square is equal to A. So this become minus 4A plus 4A. These two get cancelled. Then you will get the value of I. This is the simplified form of I plus A to the power cube minus 7A. That is option C here. The next one will be if the value of the third order determinant is 16, then the value of the determinant formed by replacing each of its elements by its cofactor. If the value of the third order determinant is 16, that is the value of the determinant is 16 in which that matrix is a third order, that is 3 by 3 matrix. So that's a 3 by 3 because we can find the determinant of only a square matrix here. So then the value of the determinant formed by replacing each of its elements by its cofactor. That means we have to find the determinant of its cofactor matrix here. So these are the options. So given that determinant A is equal to 16, where A is a matrix of order 3. So we have to find the cofactor, determinant of the cofactor. So for that we know the relation between cofactor and the adjoint here. So cofactor matrix is nothing but transpose of the adjoint matrix, or adjoint matrix is nothing but the transpose of the cofactor matrix. And also using the properties of determinant, we know that determinant of the matrix and its transpose are equal here. So using these two concepts, we write as determinant of cofactor matrix A is equal to determinant of cofactor A is nothing but adjoint A transpose. We know that transpose, determinant of transpose is equal to determinant of A. So this is nothing but determinant adjoint A. And we have one more result. Determinant of adjoint A is equal to determinant A power n minus 1, where n is the order of the matrix. Here the order of the matrix is 3. Therefore this is 3 minus 1, that is 2. Determinant of A square. Determinant of A is 16. So 16 square is 256. That is option A. The third question will be, you have to find what is the inverse of the symmetric matrix. You know symmetric matrix. Symmetric matrix is a matrix in which If you take the transpose, you will get the same matrix. That is, if A is a matrix, then A transpose is equal to A. That is known as the symmetric matrix here. So we have to choose any one of the option here. The inverse of a symmetric matrix is again a symmetric. That is A inverse. If you take the transpose, we can write the property, using the property we can write that as A transpose to the power inverse. So A transpose to the power inverse is nothing but A to the power inverse, because symmetric matrix, here this is given as, given matrix is a symmetric matrix. That means A dash is nothing but A. We can write here A here. So A to the power inverse. Transpose of A inverse is again a inverse itself. That indicates that that matrix is a symmetric matrix. Therefore, inverse of the matrix is a symmetric matrix. That is option B. The next question is, if A is a matrix, 3 by 3 matrix, this is the sum of the symmetric matrix B and a skew symmetric matrix C, then we have to find the matrix P. So these are the options here. So we know that any matrix A can be written as sum of the symmetric matrix and skew symmetric matrix here. That is, A can be written as A plus A dash by 2. This is a symmetric matrix, we know that. And A minus A dash divided by 2 is also skew symmetric, because for any square matrix A plus A dash is symmetric and A minus A dash is skew symmetric here. That means this is the matrix B according to the given data. This will be the matrix B and this will be the matrix C. We have to find the matrix B here. That is, B is nothing but A plus A dash divided by 2. Add the matrix A and its transpose, that is, interchange rows and columns of this matrix. Add these two and divided by 2. You will get this matrix. That is the option A here. The next question is, if A is a 3 by 3 non-singular matrix such that A is equal to A inverse and determinant A is not equal to 1, then we have to find the value of determinant of adjoint A. So the familiar result is determinant of adjoint A is equal to determinant A to the power n minus 1, where n is the order of the matrix. So here given that, now to find the value here we have to use the given concept, that is A is equal to A inverse. A inverse can be written as 1 divided by A. By cross multiply you will get A into A is equal to 1 here, or A square equal to 1. So we take the determinant. Determinant of A square is equal to determinant of A whole square. So both are same. These are the properties of the determinant, that is equal to 1 here. Now determinant of adjoint A is determinant of A to the power n minus 1, where n is the order of the matrix, so that is 3. 3 minus 1 is 2. So that means determinant of A square. But here by given condition we have that determinant of A square is equal to 1. Therefore determinant of adjoint A is equal to 1. That is the option A. The sixth question will be, if order of A is 2 by 3, order of B is 3 by 2 and order of C is 3 by 3, which one of the following is not defined? You have to carefully check each option here. So these are the options. The first option here, B into A into C. So order of B is 3 by 2, order of A is 2 by 3 and order of C is 3 by 3. So if I consider these two, first if we multiply B and A, so product exists, order is 3 by 3. And if we multiply with order C, again 3 by 3. So the product exists here. Second case, C into B plus A dash. So C into B. So here the number of columns of the first matrix C is equal to number of rows of the second matrix B. Therefore, product CB exists and the resultant order is of order 3 by 2. Plus again A dash is of order 3 by 2. Addition is exists here because both having same order. So the second statement is also defined. So third one. First we have to add these two matrices because these two are present in the bracket here. So first simplify the bracket. After that multiply with the matrix C. That means first we have to check the order here. So here to check the order we have to add these two matrices. So if I add here, so actually this is a addition. So if I add these two matrices, then addition exists here. Then the order will be 2 by 3 itself. Then this is the order of the matrix C, that is 3 by 3, and the order of this matrix is 2 by 3 here. So this is not possible because number of columns of the matrix C is not equal to number of rows of this value A plus B dash. Therefore, the option, this statement 3 is not correct here. If you want, you can check with the last option. Last option is this one, C times A plus B dash whole dash. That means first we have to add these two and take the transpose. So if we add these two, 2 by 3 matrix, and if you take the transpose, that will be 3 by 2. So 3 by 3 and 3 by 2 product exists. So this is also the correct statement. Therefore, the wrong statement is option C. The seventh question will be, if A into adjoint A is equal to 5 into I, where I is a identity matrix of order 3, that means A is also a matrix of order 3. By seeing this we can identify. Then we have to find the determinant of adjoint A here. Same formula, determinant of adjoint A is determinant A to the power n minus 1, where n is the order of the matrix. So we have this one, we know this one more formula, that is A into adjoint A is equal to determinant A into I. But here given that A into adjoint A is 5 into I. So using that, determinant of A is nothing but 5 here. So if I compare these two, you will get determinant A is equal to 5. So we use this formula now. Determinant of adjoint A is determinant A power n minus 1. Here n is the order of the matrix and clearly order of the matrix is 3 because here I is given, indirectly indicates that A is also a matrix of order 3 here. Then only this is possible here. So determinant A is 5, 5 square is 25. That is the option B here. Next we move to the next problem, 8th one. If A is a 3 by 3 matrix such that determinant of 5 into adjoint A is equal to 5, then determinant A is equal to. We use that in each and every problem here, determinant of adjoint here. So determinant of adjoint A is determinant A to the power n minus 1 and determinant of K into A. This is one more formula, that's equal to K to the power n into determinant of A In both the case, n is nothing but order of the matrix here. So determinant of phi into adjoint A. So if I compare with this, K is nothing but phi. Instead of A, adjoint A is there. That is equal to phi. So now here phi into adjoint A. For that, if I use this result, according to this is phi to the power 3, because order of the matrix is 3, into determinant of adjoint A. But according to the first formula, determinant of adjoint A is nothing but determinant A to the power n minus 1, that is determinant A square, that is equal to phi. This is given. So determinant of A square is equal to 1 divided by phi square. 1 by phi square is nothing but 25. 1 divided by 25. Therefore determinant of A is equal to plus or minus 1 divided by phi here. That is the option A. The ninth question is, if A is equal to determinant of this one 3 by 3 determinant and B is a 2 by 2 determinant, then we have to find what is the value of dA divided by dx, that is differentiation of this matrix A with respect to x. So this is not a matrix, differentiation of this determinant A with respect to x here. That means we have to express that in terms of B, because in all the options B is there. In terms of B, we have to express the answer. So given that A is equal to determinant, so we know how to evaluate a 3 by 3 determinant. So along the first row we expanded here. So after simplification, this will be x cube minus 3x plus 2. So this is a function of x. Now we differentiate this A with respect to x, that is dA divided by dx, differentiation of any function with respect to x here. That is this one, d by dx of A is this x cube minus 3x plus 2, that is differentiation of x cube is 3x square minus differentiation of 3x is 3. So if I take common as 3 here, then x square minus 1. And here x square minus 1. If you observe here, B is a 2 by 2 determinant. You know evaluation of the 2 by 2 determinant, that is multiply the diagonal elements minus multiply the non-diagonal elements. That means determinant is x square minus 1. So here x square minus 1, that is nothing but B here. Therefore answer is 3B. That is option B. The last question of this session will be, for a square matrix A and a non-singular matrix B, non-singular in the sense determinant of B is not equal to 0, of the same order, the value of the determinant B inverse A B is equal to. So these are the options here. Determinant of B inverse AB by using the properties of this matrix multiplication. So associative property. So associative property, the product exists here. B inverse AB, the product exists because both the matrix A and matrix B are of same order. If A is a 3 by 3 matrix, then B is also a 3 by 3 matrix. So this should be a square matrix. Here itself defined here. Otherwise B inverse given, B inverse, the inverse of the matrix exists only when that matrix is a square matrix. Therefore the product exists, therefore associative law satisfies. We interchange these two. Commutative law also satisfies. So we interchange these two. AB, we write that as B inverse A as A into B inverse. So B inverse into B, we know that matrix and its inverse, if you multiply you will get the identity matrix. So B inverse into B is I, so A into I. Any matrix multiplied by a identity matrix equal to the matrix itself. So again A. So determinant of AI is equal to determinant A here. So there is a option A. Therefore the answer will be option A. Thank you.